My name is Mohit Kumar Jangir, and I'm going to present my work towards TE-based V2V protocol for connected and autonomous vehicle. And this is a joint work with my advisor, Dr. Jisheng Lin. Let's start with the background of connected and automotive vehicles, CAV for short. This is a communication infrastructure of vehicle and its surrounding objects, where a vehicle can communicate with any of its surrounding objects. A vehicle can communicate with another vehicle, short for V2V, or it can communicate with stationary roadside unit, such as traffic signal, traffic lights, or edge server deployed on the field, and that is termed as V2I. This communication infrastructure can bring benefits of traffic safety, traffic efficiency, and energy savings. Another concept involved in our paper is trusted execution environment. This is a hardware-based solution to provide confidentiality and integrity of runtime or stored code and data. The application utilizing TEE is divided into trusted and untrusted code section. The trusted part runs inside a protected memory region called enclave. The TEE can also be utilized to secure offline data in the form of sealed data, and it can obtain dynamic secrets with remote attestation, and it can also provide trusted time, trusted GPS locations, and trusted monotonic counters for additional functionalities. Before going deep into the work, I'll provide an overview first. In our V2V protocol design, we have requirements of authentication and integrity, where any vehicle receiving the broadcast data will be able to verify the source of the broadcast data. And we also hold accountable the misbehaving vehicle based upon the data it emanates. And we also provide the privacy based upon the temporal ID generation. And all of these requirements are met with consideration of optimization and scalability. We also include a threat model of classical man-in-the-middle adversary, and we assume that she can compromise a vehicle and can access its hardware. To motivate the research problem, consider the traditional cellular or internet-based network, where the nodes are stationary or either one of the node is moving. In contrast, in the CAV communication, both of the nodes are rapidly moving, approaching, or departing. And therefore, there's a need to instantly authenticate the broadcasting vehicle. And we approach this by designing an end-to-end protocol, where a daily symmetric key is distributed to all the vehicles using remote attestation. And we leverage TE for protecting the secret data and protecting the communication. And we use time-sliced temporal ID for privacy. Let's get deep into the design phases. The first phase is the manufacturing phase, where the vehicle manufacturer and the TE designer will collaborate to fuse the TE into the onboard unit of a vehicle. In the next phase, when a vehicle is sold or resold to a new owner, the owner will take it to an automotive authority, BMW for example. And the BMW will install the enclave program into the vehicle, and it will ensure a secure boot up of that program. And then the vehicle will be provided some global parameters, one of which is the vehicle specific root key, which is unique to each vehicle. A core component of our design is the DS key renewal phase, where the BMW will hold a daily symmetric key which will be valid for a particular geography and a particular day. And any time of the day, a vehicle will request the DS key with the BMW, and with the help of TE Designer server, BMW can verify the authenticity of the TE platform in the vehicle. And after establishing a remote attestation session key, it can provision the daily symmetric key, the vehicle revoke list, and other configuration parameter. And all these secret data can be stored in the form of sealed data for security. And whenever a vehicle comes in contact with another vehicle, First, it generates a temporary ID based upon the vehicle-specific root key and a term derived based upon the time intervals. And then it can encrypt the broadcast message with the provision daily symmetric key, and the receiving vehicle can verify the integrity, authentication, the validity of broadcast message, and the revocation status of the data. And to solidify our design, we also develop preliminary prototypes. The prototype, which is designed with our proposed work, is labeled as TEE, and we compare it with the PKI-based approach, which is a traditional approach to authenticate any two nodes. And in the PKI prototype, we use three-way message exchanges. The first two message exchanges are used for key establishment, and the last one is used for the message broadcast. And note that these prototypes are preliminary because we make some assumptions, and some of the trusted modules are not implemented because of the limited support from Intel SGX. And in the results of 500 peer-to-peer broadcast and receive experiment, we can see that the PKI approach in the figure A takes about 90 milliseconds to establish a key exchange. And then in the figure B, you can see that it takes another 10 seconds to broadcast the message. Whereas in the TE case, there is no need of key exchange, and it can instantly broadcast within 13 milliseconds. So overall, we can see in the figure C that the TE takes way lower latencies than the PKI case. Before concluding, I'll briefly touch upon the related work, one of which uses TEE for generating and verifying local pseudonym certificate, or they use TEE to secure data communication within the onboard unit of a vehicle. Other related work which uses symmetric key direction, they establish a symmetric key within vehicle and a roadside stationary unit, or they establish a key between group of vehicles, or they used hash chain methods, which is proposed in the Tesla authentication protocol. And in comparison to all of these work, our design uses TE for many different phases and protection of the data, protection of the communication. And our design is not dependent on roadside units or vehicle groups or asymmetric keys. To conclude, we propose a TE-based V2V end-to-end protocol design and informally argue about basic security, privacy, optimization, and scalability requirements. And our preliminary prototype shows that the TE-based protocol could be faster and practically usable. Thank you.